Okay, let's go ahead and take a look at the atomic structure. So the structure of atoms. So what is an atom? Atom is the smallest unit of matter that retains the identity of the substance. What that actually means is if you took, let's say any element, let's say gold. If I took gold and I kept on dividing it in half and got smaller and smaller and smaller and smaller. Once I couldn't divide it anymore, that would be the smallest particle of gold that retains all of its properties. Once that property has been lost, then it would be a subatomic particle, which we'll talk about in just a moment. So an atom is the smallest piece of matter that's still that element, that atom. And the one thing I want you to pay attention to is Democritus. Democritus is the one chemist that took a look at atoms. Obviously, it was a long, long time ago. And of course, atoms, as we know, are microscopic, even smaller than that. So he didn't really look at the atom, but he was the first to propose the concept of atoms and what they meant by what an atom is and how the atoms make up everything in the world. The atomic structure. Atom is composed of two different regions or locations, and they are, as you can see, the nucleus and the electron cloud. The nucleus is the core or the center of the atom, and it contains most of the mass in the atom. And anywhere outside of the nucleus, that is the electron cloud. So that's the region that surrounds the nucleus, and it's the larger portion of the two different regions, even though the nucleus has the majority of the mass. All right, so what's actually inside of the nucleus? Okay, it contains two of the three subatomic particles. I mentioned it contains the majority of the mass. You can see 99.9%. Again, it's the center of the atom. Let's talk about the two subatomic particles that are located there. Protons are one, and protons are positively charged subatomic particles. And the neutrons are also inside of the nucleus, and those do not have any electrical charge. So those are considered neutrally charged subatomic particles. A couple other things that you want to pay close attention to about these two subatomic particles is they both have a mass. Now, it's not measured in grams or kilograms, and they get their own unit called the AMU, or atomic mass unit, and they both have the mass of one atomic mass unit. And lastly, protons, they're all identical to each other, and then neutrons are all identical to other neutrons. And the one last thing I do want to mention about the neutrons is the word isotope. Now, an isotope's definition is basically the same element with a different number of neutrons. So let's go back to our element of gold. Gold has a certain number of neutrons in it. However, there are different varieties of gold. Okay, so those different varieties are called isotopes. They either have more neutrons or less neutrons. They can't have more or less protons because protons, as we'll learn in a moment, determine what element it is. Just like there's different varieties of, let's say, apples. There's Granny Smith, Fuji, Red Delicious. They're all apples, but they're all different varieties of apples. Those would be considered isotope. So when you hear the word isotope, it's the same element. It just has a different number of neutrons than the norm would be for that specific element, or the average for that specific element in the atomic mass. We'll talk about that again in just a moment. The electron cloud. This is not a trick question. What's in the electron cloud? Well, that third subatomic particle called the electron. Okay, and now these subatomic particles have a negative charge. Okay, so they have that negative energy. And then their location determines basically where they are in there. And as you can see, extremely, extremely light. Okay, remember the mass of a proton or a neutron was 1 AMU, so it takes approximately 1,800 electrons to equal the same mass as 1 proton or 1 neutron. So let's look at our Bohr model. Our Bohr model is just a general model where you can see protons, neutrons, and electrons in any of the atoms. So again, let's start with the nucleus. Again, in the nucleus, you know at this point now that we have all of the protons and all of the neutrons for that specific element. Now, I mentioned just a moment ago about the electrons are located depending on their energy. So these are kind of like orbital paths around the nucleus, kind of like planets around the sun. So the sun was our nucleus, and all the planets will represent the rings around each of the areas. All right, so the first level, as you can see on the model here, can hold up to 2 electrons. The second level can hold up to 8. The third level can hold up to 18, and the fourth and any level thereon can hold up to 32 electrons in total. And we'll get more looking at models later on. All right, just a very quick review of our subatomic particles. Remember, protons and neutrons are found in the tiny, tiny, tiny positively charged nucleus. And again, it accounts, even though it's small, 99.9%. And notice that the nucleus is positively charged because you have a positive charge and a neutral charge. Put those together, your overall charge will be positive. The electrons found in the electron cloud, they're negatively charged. They have a relatively small mass, but they occupy that very large area outside of the nucleus known as, again, the electron cloud. All right, so lots to go over here. How do these subatomic particles balance each other? Unless otherwise stated, an atom is going to be considered neutral. If it's neutral, your positive charges have to equal your negative charges. So you can see here, if we had an element, and again, this is calcium. Calcium has 20 protons. And if it's neutral, because it didn't say it wasn't, that means it would have to have 20 electrons. Plus 20 minus 20 equals 0. Your neutrons does not have to be 20. In this case, it would be for this element. However, we know now that there are different varieties of elements. So you could have 20, but you could also have 19 or 18 or 21 or 22. Again, those are called isotopes because those are different varieties of the same element due to more or less neutrons than normal. All right, so let's go ahead and take a look at figuring out how many protons do we have in any given atom by using our periodic table. Looking at a periodic table, the top number in each box is going to represent the atomic number. And there is your definition, the total number of protons in an atom, or the number of protons in an atom. So here's a couple examples. Calcium has an atomic number of 20. So by definition, that's the number of protons. Carbon has an atomic number of 6, so it must have 6 protons. It's that easy to find out the number of protons. It's just the atomic number. The atomic number, again, which is the number of protons, identifies the atom. There's no 2 atoms or elements out there with the same number of protons, unless it's the same element. So if you have 2 protons, looking on your periodic table, you can identify that as helium. 29 protons, copper, because that is the atomic number. So finding out the number of protons, super easy. Looking at your atomic number and you're done. How about those electrons? All right, let's talk about this. The electrons are equal to the number of protons. Remember I said if it didn't say it wasn't charged, it's neutral. So the atomic number we know equals the number of protons, which is a positive charge. And if it's neutral, it would have to equal the number of electrons. Again, let's look at our example of helium. Helium has an atomic number of 2. So protons is equal to 2, and so must electrons. Another example, mercury, Hg, has an atomic number of 80. 80 is the number of protons. It's neutral, so it has to have the same number of electrons. Now this can change if the element is considered an ion, which means it's a charged atom. And we'll get that going on in a couple of days. How about the neutrons, our last subatomic particle? This one is a little bit more difficult to figure out, but not too difficult. Let's look at the atomic mass. The atomic mass is the combined total number of protons and neutrons in the nucleus. So it has a similar definition than atomic number did, but it has an additional subatomic particle, the neutrons, inside of the nucleus. So let's figure one of these out. To find the number of neutrons, you simply subtract the number of protons from the total mass. Again, your atomic mass you'll find on the bottom of each box. on the periodic table. Let's look at sodium. Sodium has a mass of 23 and an atomic number of 11. Well, I'll give you a moment to think about how many neutrons this element must have. Since we know it has 11 protons, it must have 12 neutrons because our atomic mass is 23. So 23 minus 11 equals 12. Or you can look at, down at the bottom, it says the number of neutrons equals the atomic mass minus the atomic number. Let's do a couple examples of these to make sure you understand how to do them. Let's look at lithium. Lithium has an atomic mass and an atomic number of 3. Remember, the definition of atomic mass is the total number of protons plus neutrons combined, and the atomic number is simply the number of protons. So let's do protons first. Again, based on the definition of atomic number, our protons should be 3. Our electrons, since it's neutral, is also 3. And the number of neutrons is the atomic mass minus the atomic number. 7 minus 3 equals 4. Let's do another. Iron has an atomic mass of 56 and an atomic number of 26. So take a moment, try to figure out how many protons, electrons, and neutrons are found in this atom. Protons are equal to 26 because that's the atomic number. Since it's neutral, it has to have 26 negative charges. And to find the number of neutrons, I take the mass, 56, subtract the number of protons, which is 26, or the atomic number, and I get 30 as the total number of neutrons. Let's do a couple more. Chlorine has a mass of 35 and an atomic number of 17. So figure out the total number of protons, neutrons, and electrons. Our protons and electrons are 17, since that's the atomic number, and 35 minus 17 equals 18. Let's do one more. Potassium has an atomic mass of 39 and an atomic number of 19. So how many protons, neutrons, and electrons are in this element? Again, protons are 19 because that's the atomic number and it's neutral. So you know that 19 is the number of electrons. 39 minus the 19 equals 20 neutrons. Our last thing I want to look at is putting it all together. So we have our element nitrogen. And what does it look like? Well, as you can see, I have an arrow towards the nucleus. So remember, inside the nucleus, there are protons and there are neutrons. But how many of each? As you can see, there are 7 protons and 7 neutrons inside of the nucleus because the atomic number was 7, and 14 minus 7 gives us our number of neutrons. So 7 protons and 7 neutrons. Also, hopefully you can see that I have 2 energy levels. If I have a total number of 7 electrons, then I have 2 on the first because that's how many it can hold. Now we know that the second level can hold 8, but I don't have 8 left over because I only had 7 in total. Well, 7 minus the 2 equals 5. So our total number of electrons on the second energy level is 5.